This presentation is on ribbed to roller contact ellipse truncation. The objectives for today are to review what roller bearings can have rib loads, review what roller bearings cannot have rib loads. The reason that we're doing that is just so you don't waste any time looking for rib loads in bearings that don't have the possibility of having a rib load, and to verify that you are checking the rib load, contact stresses, etc. for bearings that can have rib loads. Then we want to show what rib to roller contact ellipse truncation is, and there are two places that this can occur: at the upper rib edge and at the roller edge. And we'll give you a picture to look at that and understand what they are. Then we will look at what bearing geometry affects the rib to roller contact, and obviously then the shape of the ellipse and the possibility of truncation. After that, we'll run an example model. We'll run the load case, we'll examine the results, we'll look at the bearing details, then we'll run a parametric study on rib to roller contact ellipse truncation, altering the variables that can affect the truncation. We'll update the bearing design with the best design from the study, and then we'll examine the results once we've updated. There's actually two bearings that we're going to work with. So first of all, what bearings can have rib loads? Tapered roller bearing, anytime it's loaded, has to have a rib load, and it just deals with the basic geometry. Anytime I have a load on the outer race, it is applied normal to the roller from the surface of the the raceway. So it's applied normal and it's reacted normal. Now obviously it can be from the inner race to the outer race to the inner race. If I break this down, there's equal and opposite radial forces with regard to the center line of the roller, but there is an axial force that is additive to react the applied forces. To get that force into the roller, I have to apply a force axially at the rib. It's the only place that I can do that. Now physically, you can imagine that if you didn't have the rib in there, it wouldn't take too many revolutions and this roller would just work its way right out of the bearing. So that's really what the rib load is doing. It's keeping that roller in the bearing. The rib on the small side, or the small rib, is there only to ensure that the rollers in the cage don't fall out of the bearing. You can see that they could easily enough slide out if there wasn't a rib in there to hold it in place without the outer race in place. So bearings that can have rib loads. Cylindrical rollers are about the only ones that we're going to be looking at in that regard, and it requires that it have a rib on opposite corners. In this case, they have two ribs on the outer, one rib on the inner, and a thrust load can be taken across this roller through those ribs. Now the intent here is not that it takes a large thrust load. You wouldn't be trying to react the thrust load from a helical parallel gear set. This is really just to keep the shaft from working its way out of the gearbox. For example, if you have a gearbox running north-south in the vehicle or in the machine, and it goes down a hill, there's some gravitational forces that want to move that shaft axially out of the box. This would keep that from occurring. Then there's cylindrical roller bearings where there's two ribs on the inner, one rib on the outer. Obviously it'll take thrust similarly to the previous bearing. And then there are those that have two ribs that are integral, in this case with the outer, one rib integral with the inner, but there's a separable inner rib that can be clamped in place, so it'll actually take thrust in both directions. This one has two integral ribs on the inner, one integral rib in the outer, and a separable rib, and it will do the same thing. It'll take thrust cross corner. Now bearings that cannot take rib loads with regard to cylindrical rollers, if I got two ribs in the outer but none on the inner, there's no place to take a thrust load. Likewise, this one with two ribs on the inner, no rib in the outer, no way for it to take any thrust load. It just allows the bearing to move axially. It will slide against the surface That's what they're intended to do. So what is rib to roller ellipse truncation? I have a roller with a spherical end. So it's a spherical radius all the way around. It actually would look like it were cut out of a ball. This is completely spherical. And it's making contact with the rib. The rib's at a bit of an angle. This is the point of contact. Due to the load that's applied, it creates this ellipse. Now, as long as that ellipse is between the chamfer and where the corner radius of the roller is, it's contained. However, when it extends beyond this edge, this corner radius, it's rib to roller contact ellipse truncation at the roller edge. If the contact ellipse goes above the chamfer here, then it's rib to roller contact ellipse truncation at upper rib edge. So it's the rib edge or roller edge. If the chamfer were smaller or the rib OD made larger, so if I move this up or made this a smaller chamfer, if I made it small enough, you can see that I could get rid of the problem I have here with the rib to roller contact ellipse at the upper rib edge. However, this doesn't do anything to my lower edge, my lower truncation, rib to roller contact ellipse truncation at the roller edge. At the roller edge, as the roller spherical end radius gets smaller, or the curvature gets to be a smaller radius, so there's more drop at the ends, the contact moves away from the inner race. So this point moves further up as that spherical radius gets smaller. And that is a value of H. H is measured from this theoretical corner to the center point of the contact. As the rib angle gets smaller, gets closer to perpendicular, the center of the contact moves away from the inner race. Again, H is getting larger. So, of course, vice versa. If this spherical end radius gets larger, that drives the contact angle closer to the corner. And if the rib angle gets larger, that drives the point of contact closer to this toward the raceway. So we will look at first modifying the spherical radius and rib angle, and then we'll actually look at moving this rib up and giving us some more room to work with to try to get the ellipse between these two limitations. And that we will be doing in this example model. This model is just a single shaft, pair of tapered roller bearings on it with a point load applied. And it's a radial load, axial load, and moment load applied at that point. A bit of torque applied through the shaft, not that that has any effect on the bearings. Now, as far as this duty cycle is concerned, there's just one load case. We'll call it the worst load. So we look at the report for the bearing. And I'll increase this, make it a little easier to read. I have the worst rib contact ellipse truncation is 43.8% and 43.7%. So I have some problems with truncation of the ellipse between the rib and the roller end. Here you can see what the maximum stress is. It's only 14 megapascals, but I have nearly half of it is being truncated, and that's the maximum. There is also a minimum rib contact ellipse truncation that could be from 0 to 43.7%. I don't know what it is at this point. And for bearing 2, 43.7% ellipse truncation maximum and 20 megapascals contact stress. So now we'll have to look at the details of these bearings. And I know from doing this that if I just turn on the stress contour can see my results right away. My maximum rib to roller ellipse truncation at the upper rib edge is 43.8, and at the roller edge it's 34.9. So I'm pretty close to 80% truncation. So my 14 megapascals is not it cannot be a valid number, because the assumption is that there's no ellipse truncation. With that much truncation, I don't have any idea how bad it actually, or how high it actually is. Now for bearing 2, I'm actually a little bit over 80% truncation, between the 43.7 and 37% truncation. So again, I have a lot of truncation. So we'll start with bearing 1. That's this bearing. I go down here, you can see that I have a large and spherical radius, that's RSP, is 125, and the angle F is 1 degree. We'll take a look at what that actually looks like in here and give you some additional information. So the large and spherical radius is 125. In this picture, you can see RSP, roller spherical radius, is this surface, and the angle F over here, perpendicular to the roller's axis of rotation to the theoretical sharp corner, the rib angle is given as F. So we're going to modify these two values. Now I could go through and try a bunch of values and do a different, just keep trying numbers till I get results that work. The problem is I won't really have a value that has a range on it. I will have a single point that I know that works, but I don't know if it's manufacturable. For example, if it were 1 degree, I don't know if that's 1 degree is my minimum value, my maximum value, or nominal value. For manufacturers normally need some sort of manufacturer range for the radius. Likewise, they need a range for the spherical radius at the end. So I have already set this parametric study up, and we will go through it. Now right now it is set up to 9 steps full factorial. The variables, as I said, is RSP and R. Now because this is a custom bearing, I have to show the catalog data. I go to catalog data, the 30212 CR bearing is bearing 1. And I go down here and find my roller end spherical radius and my rib angle to raceway. So for the roller end spherical radius, now I gave it the name bearing 1, roller end radius. I'm going to go from 40 to 200, so that'll be 9 steps at 20 millimeter increments, because I've set it up as the method is 9 full factorial. Now the rib angle, bearing 1 rib angle, I'm going from 1 to 3 degrees, so it'll be 9 steps in 0.25 degree increments, or 1/4 degree increments. So those are my variables I want to deal with. Now action, what do I have to do? Well, all I have to do is have it run the static analysis. So I run the static analysis, it'll calculate, among other things, the raceway end stress. So what do I need it to do? Sorry, I had to go to, for bearing 1, for the load case I want to look at, which there's only one, and that's worst load, I want to find the maximum rib contact ellipse truncation. I gave it the name bearing 1, roller to rib ellipse truncation. And what do I want to do with it? Well, I want to minimize it, and my target value is 0%. So now it will run, after I click run, it will run 81 cases and give me all the values or the results for all of those. Now, the easiest thing to do is view this as a 3D chart. Normally you should wait until it's done running before you try to bring up this 3D chart. If you push it too hard, you will get it to fail, and you'll have to start over again with the duty cycle, or with the, parametric study. So it's ran all 81 load cases, updating the data. Now, this is a scatter 3D plot, and I want to view it from the top. The reason being, there's some data in here that didn't solve. And if I look at my report, now by default it goes to 10. I need to make it 81 so I can see all my data. The way this is set up, anytime I exceed 50% truncation, it fails or it doesn't solve. So these load cases that are showing a value in here in red have more than 50% truncation of the ellipse. And that's why there's no data that's valid in here. It didn't plot the data. Now, unfortunately, rather than not show the data at all, it assumes 0. So this data in here is invalid. Now, what am I looking for? I want to find a nice area that's square, because my tolerances are plus or minus for the rib angle and plus or minus for the roller end radius. So I need to find a flat area in here that solves and gives me enough range on rib angle and spherical end radius. Now, I've looked at this earlier. Now, what I do want to pick up some values that I know don't work, so that I have know how far out I can push this. So I'm going to go down to a radius of 50, and I'm going to go up to, this is 1.75, so I'm going to go down to 1.7. And then at the upper end, I got a lot of area in here that's pretty good, but I see that I have some bad, but I'll go up to 90, and I can see that I have a lot of area in here that looks good, so I'm going to make this out to 3.5 degrees. I don't have that actual data, but it looks like that should work. So if I close this, I can go back to my variables, and on the rib angle, I'm going to give it discrete values. So I'm going to give it a range of 1.7 to 3.5, and I'm going to go in 0.1 degree increments. So it's giving me that value, or these values automatically as a range. Now the roller end radius, I'm going to do something very similar. I looked at a minimum of 50 to 90, and I'll use 5 millimeter increments on that. So I've just altered my variables, everything else remains the same, and I can tell it to run. Now there's 171 steps to this. Now I'm going to take a chance and push it again. And I do know that if I try to rotate this picture at this point, that it will cause a problem. So I have 171 steps to run. So this would be a good time to go get a cup of coffee if you were doing this. Fill up your cup, come back. But it just fills in the data. About all we can do is just wait for it to solve. It's the problem with a live demo. I can't speed up these results. when I'm looking at this chart, I want to view it from the top. I just right click in this area in here. So that's how I access the chart options to view it from the top. So if I right click, I have view and top. So I have about, 3 points of data that are invalid, this one and these two. So anything over here is invalid, but looks like the rest of the data is good. So we'll view it from the top again. So you have quite a nice blue area that I can deal with. And looks like I can go from 50 to 70. All right, that's pretty good. And I can go over as far as, now that's 2.25, so if I went down to 2.3 and to 3.5. So that gives me a decent manufacturable range. So what I'm going to use is the nominal of that. So about, it'd be 2.9 and 60. So that's right about in the middle, 2.9 and 60 is right here, roughly. I want to find that candidate in here. Now it's not my top candidate, and by default it just shows the top 10. So if I put the number in here of 171, I'll slide it down here so we can see the points at the end that didn't solve. I'm looking for 2.9. Notice it goes, this moves along and then does the increments and runs through everything. But 2.9 and 60, that's candidate 111. So why am I concerned about that? If I can find candidate 111, I highlight it, tells me candidate 111, 2.9 degrees and 60 millimeters, that's the one I want. I can click on this button over here that says apply, and it will change my bearing data. So let's take a look real quick. 2.9 and 60. It's been updated. We want to go into the details just to verify that that's what it's in there. 60 and 2.9. Now actually it's 2.9, a whole bunch of zeros, 9. Program works in radians and converts back to degrees. So that's why you're seeing that. So I've taken care of that bearing. Now let's look at bearing 2. I'm dealing with 150 and 1. So we'll run a parametric study just like we did before. And I have the parametric study set up just like I had before. 9 steps, full factorial, variables, catalog, custom catalog. We're looking for rib angle and roller end radius. And just like before for the rib angle, now it's bearing 2 rib angle, 1 to 3 degrees. That seemed to be a decent range to deal with. And the roller spherical end radius of 40 to 200. Again, the action is to run the static analysis for the load case we're concerned about, which in this case is just worst load is the name of that duty cycle. And my target is the maximum rib contact ellipse truncation with a target to minimize it shooting for 0%. So I'll run the analysis. So 81 steps to this, just like there was before with the full factorial. See if I can get this to work without crashing. Again, we just have to wait for it to solve. For all 81 load cases and plot the data. Plots it rather quickly. I have a couple of areas in here that didn't solve that are fairly large, so I don't have a lot to deal with as far as area that's available. So let's see what it looks like. And I've got a very small valley. It's more of an ellipse that as far as tolerances, I can't really tolerance to that. My tolerance area needs to be square. So if you remember, I can change the rib diameter to give me more room for ellipse truncation at the rib chamfer. So one of these is rib chamfer and one of these is the roller edge. I believe this is roller edge and this is rib chamfer. So let's make that change to the bearing and rerun this analysis. So the large rib shoulder diameter, D1 is that value, that's that diameter. It's 59.5, and I'm going to change it to 62. That's only 2.5 millimeters on diameter. That's 1.25 millimeters per side. That's not a lot. Make sure you select OK. Otherwise, you don't get the change and you'll just rerun the same analysis that we ran. I'm just going to load the parametric study. We looked at what was in it before and we will just run it. Unfortunately, you do have to wait for all 81 times for the program to run. And again, we will view it from the top. I've got this area that's invalid, but I've got data in here that at least I can deal with. Let's see what that looks like. Alright, so 100 seems to be a pretty good top end in here, and I've got some width to it. I can get down to 40, and that allows me to pick up some bad or some data that doesn't work. So if I go down to it's 1.25, so 1.3 to 2.3 and 100, that looks like that'll give me enough data or enough area to work with some data. So for the spherical end radius, again, I'm going to put in discrete values in a range of 40 to 100 in 5 millimeter increments. And on the rib angle, going from 1.9, I wanted to go 1.2 to 2.3. And that was 1.3, that's right, 1.3 to 2.3 in 0.1 increments. $143 runs. And it isn't that important which way I go with rib angle and roller end radius. Those are just the two of the coordinates that make up the X and Y. The Z is the magnitude, so it doesn't matter if this is X or Y or this is X or Y. And view it from the top. All right, I've got all good data. So 65 to 90. I can go from my 1.3 to 2.3. I can use my full range. So maybe at this point I would, well, I can see that it's dropping off, that is headed in this direction. So all it would do is narrow up my radius. So if I go from 90 to 65 and 1.3 to 2.3, so I'm going to use 1.8, and well, it comes out to be what, 77.5. That isn't going to be one of my candidates. So I'll use 1.8 degrees and 80 millimeters. So we find 1.8, 80, it's candidate 74. So we find candidate 74, 1.8 and 80. We'll apply that. And we'll just check it to be sure it's in there. 80 and 1.8. Now, if I wanted to, I could put in the 77.5 degrees in here. I'm going to edit the details, internal, and make this 77.5. Now, I don't know, it kind of depends on what the manufacturer has for tolerances and ranges. I'm not going to keep that. I'm just going to hit cancel. Just when I hit cancel, it stays as 80 and 1.8. So now we'll run the static analysis and check this. Fortunately, we just have to wait for it to run through all of this. For the values that we need, we really don't need to have this, but that's the way the program's set up. So it runs everything, and then it doesn't have to run anything again later on. So ellipse truncation at the upper rib edge is 0, and at the roller edge is 0. My stress is 347 megapascals. And for bearing 1, we have no truncation of the contact ellipse between the roller and the rib. The upper rib edge at 0, and at the roller edge at 0. So now we have a valid design that prevents rib to roller ellipse truncation. So that's my presentation for today. Does anybody have any questions? Just please fill in the box, and I'll be able to see them and see what your questions are. Okay, what is the basis of the stress safety factor for the rib to roller contact? Let's just go to the bearing report. Okay, we're showing a maximum rib contact stress of 489 megapascals. The rib safety factor is 8.183. So if I multiply 8.183 times the 489, you'll find that it's basically 4,000 megapascals, the same stress limit that the raceway has. So that's a way to check it, but it is the same as what is used for the raceway, and that's where that actually comes from. Okay, I have another question. What is the geometry of the roller and rib contact? So that they want to know what is the geometry and the semi-minor and semi-major axes of the contact ellipse. I have a picture that I had when I was working on that. All right. The end of the roller is basically a ball, and the rib is radially straight but wrapped around the bearing. Actually, this is not the best picture. Let me get this one. It's a conical surface, but you're on the inside of the cone is where the ball is, or the roller is actually running against. Radially it's straight, but it's at an angle and rotated. So that is what the contact looks like in general. And when you do the stress analysis, you have to go put two planes through the line of contact. Now that's a bit of an angle rather than horizontal. It's a bit of a down angle. But radially, it's a straight line on the ball radius, and then when I go 90 degrees to that, it's the ball radius, and then that's where my picture comes in. When I go from across the race, you see cut through that ball, it's a very large radius. Now it's probably more of an elliptical surface. I really didn't run any numbers on it. I was just trying to make sure I knew what it looked like. So as long as I can figure out what the curvature is in this very small area, for practical purposes, that's a radius. As far as where the semi-major is, because this surface cups the ball, that'll be the direction of my semi-major axis of the contact ellipse. We really don't break it down to semi-major and semi-minor as far as the analysis, but it wraps the ball in this direction, so there would be my semi-major axis, because it's a ball on a flat plate, basically in the other direction. That would be the direction of my semi-minor axis. Hope that makes sense. Any other questions? All right, if there are additional questions, there will be some information on where to send those, and we'll get back to you. Thank you very much for your time. Have a good day.